Picture standing on the coast of Europe in the year 1818, staring at a sky darkened not by night, but by something far more unsettling. The sun, hidden behind a veil of ash, casts eerie red hues across the land. Crops fail, temperatures plummet, and no one knows why until whispers spread of a distant explosion, so powerful it altered the very rhythm of the seasons. This wasn't just bad weather, this was history rewriting the climate itself. We often think of weather as something that happens to us, an unpredictable force shaping civilizations through storms, droughts, and shifting winds. But what if I told you there are moments when the opposite occurred? Moments when human actions or colossal natural events tied to our past reached up and twisted the skies themselves. From volcanic eruptions that plunged continents into winter to wars that unintentionally redirected rainfall patterns, history is riddled with turning points where the weather didn't just influence events influenced the weather. This video isn't just about disasters or odd meteorological phenomena. It's about the hidden threads between human ambition and the atmosphere, 30 astonishing cases where history and climate collided in ways that still echo today. You'll hear about empires toppled by their own environmental mistakes, battles won or lost because the wind changed direction at the perfect moment, and even how a single ship's journey might have cooled the planet. These stories blur the line between natural and man-made, revealing how fragile our relationship with the elements truly is, and how a single event can ripple across centuries. So settle in, the forecast for today's journey: unpredictable, extraordinary, and utterly unforgettable. On April 10, 1815, Mount Tambora erupted with such force that it literally tore itself apart. The blast was heard over 1,000 miles away, and the ash it spewed into the atmosphere blotted out the sun for days. But the real catastrophe unfolded slowly as volcanic particles circled the globe, scattering a fine veil that dimmed sunlight and disrupted weather patterns for years. By 1816, the effects were impossible to ignore. Temperatures plummeted, frost struck in July, and snow fell in New England during summer months. Farmers watched helplessly as their crops withered, leading to food shortages so severe that desperate families in Europe resorted to eating weeds and tree bark. The chaos wasn't just agricultural. In Switzerland, a group of writers trapped indoors by relentless rain and cold turned to storytelling to pass the time. Among them was Mary Shelley, whose feverish imagination birthed Frankenstein, a tale as dark and stormy as the weather outside. Meanwhile, in China, unseasonable cold killed rice harvests, triggering mass migrations and unrest. Even North America felt the strain, with Thomas Jefferson writing about the year of famine from his Virginia estate. What makes Tambora's legacy so chilling isn't just the scale of destruction, but how it reveals the fragile threads tying human society to the climate. A single eruption didn't just alter the weather. It rewrote history, sparking creativity, desperation, and even revolution in its wake. And while we often think of volcanoes as forces of local destruction, Tambora proved they can reach across continents and centuries, turning the sky itself into an agent of change. Now picture a different kind of storm, one not born from fire and ash, but from human error and an unrelenting drought. In the early 1930s, the Great Plains of America, once hailed as the nation's breadbasket, transformed into a swirling nightmare of dust. Skies turned black at noon as towering walls of dirt, some thousands of feet high, rolled across the land, burying homes, choking livestock, and stripping the soil bare. This wasn't just bad weather. This was the Dust Bowl, a man-made catastrophe that reshaped the climate of an entire region and forced hundreds of thousands to abandon their land in search of survival. The roots of the disaster stretched back decades. In the early 20th century, settlers flocked to the plains, lured by promises of fertile soil and cheap land. With new farming technology, they plowed under the native prairie grasses that had held the earth in place for centuries, planting endless rows of wheat. When rains were plentiful, the fields flourished, but no one accounted for the region's cyclical droughts or how stripping away that natural armor would leave the soil defenseless. By the 1930s, drought returned with a vengeance. Without deep-rooted grasses to anchor it, the dry topsoil simply blew away, carried eastward by relentless winds. Dust storms became so frequent that children wore masks to school, and families stuffed wet rags under doors to keep the grit from invading their homes. The devastation went far beyond ruined crops. The dust infiltrated everything, clogging engines, seeping into food, even causing fatal dust pneumonia. In Oklahoma, Texas, and other affected states, entire communities packed up their few belongings and fled westward, becoming known as Ockies in California, where they faced prejudice and grueling labor in migrant camps. John Steinbeck immortalized their plight in The Grapes of Wrath, but the real toll was even grimmer: broken families, abandoned farms, and a landscape so scarred it would take generations to heal. Yet the Dust Bowl didn't just alter lives, it altered the weather itself. Scientists later discovered that the massive plumes of dust actually disrupted atmospheric conditions, reducing rainfall even further in a vicious cycle. The storms carried soil as far as New York City and even out to ships in the Atlantic, proving how deeply human actions can disturb natural systems. And the lessons learned led to revolutionary changes in agriculture. Contour plowing, crop rotation, and soil conservation programs aimed at preventing such a disaster from ever happening again. What makes the Dust Bowl so haunting isn't just the scale of suffering, but the stark reminder that the land doesn't forget. When we disrupt delicate balances, the consequences ripple outward, twisting weather patterns and rewriting futures. It's a story of hubris, survival, and ultimately, resilience, one that still echoes in today's debates over climate change and land management. Because the next time the skies darken with something other than rain, we might not be able to blame nature alone. Imagine a world where the Thames River in London froze so solid that frost fairs erupted on its ice, complete with makeshift shops, roasted meat stalls, and even ice skating. This wasn't a fleeting winter wonderland. It was the chilling reality of the Little Ice Age, a mysterious climatic shift that gripped the Northern Hemisphere for over 500 years, starting around the year 1300. Rivers that had flowed freely for centuries turned to highways of ice. Vineyards in England, once thriving, withered as summers grew shorter and colder. In the Alps, glaciers advanced relentlessly, swallowing entire villages whole. And while this wasn't a true ice age on the scale of prehistoric eras, its impact was profound enough to reshape economies, cultures, and even the course of history. What caused this centuries-long cold snap? Scientists point to a perfect storm of natural factors, a cluster of massive volcanic eruptions, like the one at Mount Samalas in 1257, spewed sun-blocking ash high into the atmosphere, dimming global temperatures. At the same time, solar activity entered a quiet phase known as the Maunder minimum, where sunspots became rare, reducing the sun's warmth even further. These forces combined like a climatic lock, trapping the Northern Hemisphere in a prolonged shiver. The consequences were staggering. In Europe, crop failures became routine, leading to famines that left villages desolate. The Norse colonies in Greenland, once verdant enough to justify their name, found themselves isolated as sea ice expanded, cutting off supply routes. By the 1600s, Dutch painters like Hendrik Averkamp were capturing scenes of daily life on frozen canals, while in Switzerland, terrified villagers pleaded with clergy to perform exorcisms against the advancing glaciers. Even warfare felt the chill during the brutal winter of 1708. Swedish troops marched across a frozen Baltic Sea to invade Denmark, turning the ice itself into an unexpected battlefield. Yet the Little Ice Age wasn't just a story of suffering. It also sparked innovation. The Dutch, masters of adaptation, refined ice skates and windmill technology to harness the cold winds. In England, the scarcity of grape harvests pushed brewers to perfect beer making, fueling a cultural shift toward ale. And some historians argue that the cold's economic disruptions may have indirectly fueled revolutions as hungry populations grew restless under ineffective rulers. What makes this era so fascinating isn't just the dramatic weather, but how societies responded, sometimes with resilience, sometimes with desperation. The Little Ice Age reminds us that climate isn't a backdrop to history. It's an active player capable of toppling kingdoms, inspiring art, and forcing humanity to adapt in ways we're only beginning to understand. And as we face our own climate challenges today, those frozen centuries offer a stark lesson. When the world grows colder or warmer, civilizations must change or collapse. The summer of 1783 should have been a time of abundance across Europe, but instead the skies turned hazy, the air reeked of sulfur, and a strange dry fog crept over the land, blocking out the sun's warmth. Birds fell dead mid-flight, leaves withered on trees as if scorched by invisible fire, and when the first reports trickled in from Iceland, the truth became terrifyingly clear. A volcanic fissure named Laki had torn open, unleashing one of the most destructive eruptions in recorded history. For 8 agonizing months, it spewed not just lava, but a suffocating cocktail of toxic gases enough to poison the atmosphere of an entire continent. The numbers stagger even today. Laki ejected an estimated 120 million tons of sulfur dioxide into the air, forming acidic particles that rode wind currents southward. When these particles mixed with water vapor, they created acid rain so potent it burned crops and contaminated soil. In England, farmers documented wheat stalks blackened as if dipped in ink. Across France, vineyards yielded grapes shriveled to bitter husks. Livestock succumbed by the thousands, their lungs ravaged by fluoride-laced air. Contemporary accounts describe cattle collapsing in fields, their bones so brittle they shattered under their own weight. But the devastation wasn't just ecological. As food prices skyrocketed, famine gripped Europe's poorest communities. In Paris, bread riots erupted as desperate families clashed with bakers accused of hoarding flour. Some historians now draw a direct line between Laki's climate chaos and the powder keg of discontent that fueled the French Revolution 6 years later. After all, how do you convince starving peasants to respect a monarchy when their children's bellies are swollen from hunger? Even Benjamin Franklin, then stationed in France as a diplomat, noted the eerie weather in his journals, speculating that volcanic haze might be altering the climate, an astonishingly prescient observation for the 18th century. Yet Laki's most haunting legacy lies in its scale. Unlike Tambora's single catastrophic explosion, this was a slow, creeping disaster, its effects amplified by the sheer duration of the eruption. Imagine living under that oppressive haze for months, watching each sunrise dimmer than the last, unsure if the world would ever feel normal again. It's a reminder that nature's fury isn't always dramatic bursts. Sometimes it's a silent, suffocating grip, tightening until societies crack under the pressure. And while we'll never know exactly how many lives Laki claimed indirectly, one thing is certain: when the earth itself becomes a weapon, the weather is just the first casualty. By the mid-14th century, Europe was a continent on the brink not just of human suffering, but of environmental transformation. When the Black Death arrived in 1346, carried by flea-infested rats on merchant ships, no one could have imagined that the devastation left in its wake would reach beyond emptied villages and piled corpses to alter the very composition of the atmosphere. Over the next 7 years, the plague wiped out an estimated 1/3 of Europe's population, creating an eerie silence where bustling towns had once thrived. But in that silence, something unexpected began to happen. Fields once cleared for crops grew wild, untended by hands lost to the pestilence. forests crept back over abandoned farmland, their roots sinking into soil that hadn't felt such cover in centuries. And as these trees multiplied, they began to siphon carbon dioxide from the air on a scale large enough to leave a mark on the global climate. This wasn't just ecological recovery, it was a planetary feedback loop. With fewer people to tend the land, vast stretches of Europe reverted to woodland, absorbing enough CO2 to trigger a detectable cooling effect. Ice cores drilled from glaciers in Greenland later revealed a dip in atmospheric carbon during this very period, while historical records from the Alps note glaciers advancing as temperatures dropped. Some climatologists now estimate the planet cooled by roughly half a degree Celsius, a seemingly small shift, but one with outsized consequences. Across the North Atlantic, Norse settlers in Greenland found their already marginal farming conditions growing harsher, while European vineyards reported later harvests and weaker yields. Even the art of the time reflects the change, with painters like Pieter Bruegel the Elder depicting frost-laden landscapes and icy revelry that would have been unthinkable a century earlier. Yet the Black Death's climate legacy is more than a grim scientific footnote. It's a stark demonstration of how intimately human activity is tied to the environment, and how quickly the planet can respond when that activity shifts. For centuries, medieval farmers had hacked back forests to feed growing populations, releasing stored carbon into the air. The plague reversed that process in a matter of years, offering an accidental preview of what large-scale reforestation might achieve. Modern researchers studying this period call it the Great Dying Carbon Sink, a haunting case study in how catastrophic human loss can inadvertently cool the Earth. Of course, no one would suggest pandemic as a climate solution, but the episode forces us to reckon with an uncomfortable truth. Sometimes, nature's most profound corrections come wrapped in tragedy. What makes this story so chilling isn't just the scale of death, but the reminder that our planet keeps score. The same forests that regrew over abandoned villages also quietly drew down enough CO2 to shift temperatures, proving that even in humanity's darkest hours, the atmosphere records our presence or our absence. And as we face our own climate crisis today, the Black Death whispers a warning from the past. The Earth responds always to what we leave behind. When Christopher Columbus stepped onto the shores of the Caribbean in 1492, he wasn't just bridging two worlds, he was unwittingly setting off a biological chain reaction that would rewrite the planet's climate. The Columbian Exchange, as historians now call it, wasn't merely about ships carrying tomatoes to Europe or horses to the Americas. It was a vast, silent experiment in planetary engineering, one that reshaped continents so profoundly that the atmosphere itself responded. Over the next 2 centuries, the transfer of crops, livestock, and most devastatingly diseases between the hemispheres triggered a cascade of ecological changes. Forests regrew where civilizations had collapsed, farmlands vanished under waves of new vegetation, and by the 1600s, some scientists believed this global reshuffling of life may have cooled the Earth enough to leave a fingerprint in the climate record. Consider the scale of transformation. In the Americas, European diseases like smallpox ravaged indigenous populations, with mortality rates in some communities exceeding 90%. The consequences were ecological as much as human. Vast stretches of cultivated land, once tended by millions, were suddenly abandoned. In the Amazon, terra preta, fertile soils painstakingly enriched by indigenous farmers slowly vanished beneath regrown rainforest. In North America, the collapse of agricultural societies allowed forests to reclaim maize fields from the Mississippi Valley to the Great Lakes. All that regrowing vegetation began absorbing carbon dioxide at an unprecedented rate, potentially sucking enough of the greenhouse gas from the atmosphere to nudge global temperatures downward. Meanwhile, across the Atlantic, the exchange was having the opposite effect. European farmers eagerly adopted New World crops like potatoes and maize, which thrived in soils too poor for traditional wheat or barley. These high-yield staples fueled population booms, requiring even more land to be cleared for agriculture. But the real climate twist came from an unexpected player, the humble earthworm. Accidentally transported in ship ballast, invasive worms spread through North American forests, breaking down leaf litter at an unnatural pace, a process that released stored carbon back into the air. It was a perfect atmospheric seesaw, one hemisphere becoming a carbon sink while the other leaked emissions. The most compelling evidence for this climate shift comes from ice cores. Samples from Antarctica and Greenland show a puzzling dip in CO2 levels during the 1600s, coinciding exactly with the peak of population collapse in the Americas. Some researchers estimate the regeneration of forests alone could have removed enough carbon to cool the planet by up to 0.15 degrees Celsius, a small but meaningful change in an era already gripped by the Little Ice Age. The timing is uncanny. Temperature records from Europe's vineyards and China's lake sediments reveal colder growing seasons right when the Columbian Exchange's ecological ripples would have been most intense. Yet this story isn't just about gases and glaciers. It's about how deeply human societies are woven into the fabric of the climate. The same ships that carried conquistadors and missionaries also carried invisible passengers, seeds, spores, and pathogens that unwittingly terraformed the planet. When indigenous fire practices ceased in the Americas, the reduction in smoke may have even altered cloud formation. When European sheep grazed on Andean hillsides, their hooves compacted soils in ways that changed water absorption for centuries. Every choice, every accident echoed through ecosystems. What makes the Columbian Exchange so haunting isn't just its role in cooling the globe, but its reminder that climate change isn't a modern invention. Long before smokestacks and tailpipes, humanity was already bending the atmosphere to our will, or in this case, our blunders. The forests that regrew over abandoned temples and villages didn't just hide history. They absorbed enough carbon to leave a mark in ice cores thousands of miles away. And that's the unsettling lesson here. Sometimes the weather doesn't just shape civilizations. Civilizations, through their rise and fall, shape the weather right back. Picture the English countryside in 1760, where rolling fields are still plowed by oxen and candles light homes after dark. Now fast forward just 80 years, smokestacks dominate city skylines, steam engines rattle across iron tracks, and a perpetual haze of coal smoke hangs over London like a shroud. This wasn't just progress, it was a planetary turning point. The Industrial Revolution didn't just change how humans worked, it changed how the Earth breathed, marking the moment we began pulling ancient carbon from the ground and pumping it into the sky at a scale nature had never seen. Coal was the engine of this transformation. For centuries, it had been dug in modest amounts for local hearths and blacksmiths. But with James Watt's improved steam engine in 1769, demand exploded. Factories no longer needed rivers for power. They could burn coal anywhere, anytime. By 1800, Britain was consuming over 10 million tons annually, a figure that would triple by 1850. The consequences weren't just economic. Each lump of coal burned released carbon dioxide trapped underground since the Carboniferous period, 300 million years earlier. And unlike volcanic eruptions or forest fires, this wasn't a temporary spike. The furnaces never stopped. The first signs of disruption were subtle. In 1815, while Tambora's eruption brought global chill, a Swiss scientist named Jean-André Delac noticed something odd. Winters in Geneva seemed milder than his childhood memories. He blamed deforestation, unaware that coal smoke might be trapping extra heat. By the 1830s, naturalists marveled at London's peculiar pea-soup fogs, thick yellow clouds that reeked of sulfur and blotted out the sun for days. These weren't natural formations, they were the atmosphere choking on humanity's exhaust. Ice cores from Antarctica now reveal the precise moment the balance tipped. Around 1800, atmospheric CO2 levels stable for millennia at 280 parts per million began an unbroken climb. Tree rings from stressed oaks in Germany show slowed growth as pollution increased. Even the oceans responded. Coral skeletons from the Great Barrier Reef bear chemical signatures of coal ash washed downstream from Australian mines. The planet, in essence, started keeping receipts. What makes this era so pivotal isn't just the scale of emissions, but the irreversible threshold it crossed. Before the Industrial Revolution, climate changes were regional or temporary. A volcano's cold snap here, a solar minimum there. But coal introduced something new, a steady, human-made pressure on the climate system that accumulated year after year. By 1850, global temperatures had crept up roughly 0.2 degrees Celsius, small compared to today's crisis, but the first undeniable nudge in a warming trend that would accelerate exponentially. Yet the most haunting legacy lies in the choices made knowingly. As early as 1861, Irish scientist John Tyndall proved that CO2 trapped heat, warning that industrial emissions might one day alter the climate. His contemporaries dismissed it as speculation after all. How could puny humans affect something as vast as the atmosphere? That blind spot, more than any steam engine, set the stage for our current crisis. Because the Industrial Revolution didn't just invent machines, it invented a worldview where nature was infinite, disposable, and forever at humanity's command. And 2 centuries later, we're still living with the weather it made. On the morning of August 27, 1883, a sound ripped through the air so immense it circled the globe 4 times. 3,000 miles away on the island of Rodriguez in the Indian Ocean, a police chief scrambled to investigate what he assumed was cannon fire from a nearby ship, only to discover no vessels in sight. The source of the noise, the obliteration of Krakatoa, a volcanic island between Java and Sumatra, vanishing in the most violent explosion in modern history. When the dust settled literally, the world would spend years grappling with the aftermath, as ash high in the stratosphere painted sunsets so lurid they inspired artists and terrified farmers alike. The eruption's raw power defies imagination. The initial blast was 200 megatons, 13,000 times stronger than the atomic bomb, dropped on Hiroshima, shattering the island into fragments and triggering tsunamis that drowned 36,000 people along nearby coasts. Shockwaves leveled forests 50 miles away, and barometers as far as London spiked from the atmospheric disturbance. But the most far-reaching impact wasn't the destruction on the ground. It was the 21 cubic kilometers of ash and sulfate aerosols launched 50 miles into the sky, where stratospheric winds caught and spread them like a creeping veil across the planet. Within weeks, the optical effects became undeniable. Sunlight filtering through these high-altitude particles scattered blue light, leaving sunsets awash in fiery reds and oranges so intense they looked like the sky itself was burning. From New York to Paris, newspapers documented the phenomenon, with one Londoner describing twilight as a luminous crimson like the glow of a furnace. Painters like William Ashcroft raced to capture the lurid hues in real time, creating hundreds of pastel sketches that now serve as a scientific record of atmospheric pollution. Even Edvard Munch's The Scream, with its blood-red sky, may have been inspired by Krakatoa's lingering aftermath over Norway, yet these stunning displays came at a cost. The same particles that colored the skies also blocked sunlight, enough to drop global temperatures by over 1 degree Celsius for nearly 5 years. Crops faltered under weakened summer rays, vineyards recorded delayed harvests as far away as California. In 1888, a massive blizzard dubbed the Great White Hurricane buried the northeastern United States under 50 inches of snow, a storm some climatologists linked to Krakatoa's atmospheric disruption. And the ash had stranger side effects. Moonrises occasionally appeared electric blue, as finer particles selectively scattered red light away from the lunar surface. Perhaps the most eerie legacy lies in the human response. With no understanding of stratospheric circulation, many interpreted the vivid sunsets as divine omens or apocalyptic signs. Religious revivals surged in parts of Europe, while pseudo-scientific journals speculated about cosmic disturbances altering Earth's orbit. Only later would scientists realize the truth, that a single geological event could weave itself into the planet's climate like dye through fabric, leaving a mark visible from every corner of the globe. Krakatoa didn't just explode, it demonstrated for the first time on a global scale how tightly connected Earth systems truly are, where a catastrophe on one side of the world could ripple into the daily lives of millions who'd never heard its name. And those blood-red sunsets, they weren't just beautiful anomalies, they were the sky whispering a warning about how fragile our atmosphere really is. December 5, 1952 began like any other chilly winter morning in London. Residents stoked their coal fires against the damp cold, factories belched smoke into the leaden sky, and the usual yellow-tinged fog settled over the city. But this was no ordinary London fog. Over the next 5 days, an unprecedented atmospheric nightmare would unfold, one so thick it blinded pedestrians in broad daylight, so toxic it killed cattle in their stalls, and so lethal it would claim as many as 12,000 lives before the air cleared. This was the Great Smog, a catastrophe that exposed the deadly price of industrial progress and forced the world to confront the very air we breathe. What made this smog different was a perfect storm of weather and human activity. A high-pressure system parked itself over southern England, creating an inversion layer that acted like a lid over the city. Normally, smoke would rise and disperse, but now it became trapped at ground level, mixing with moisture to form a noxious cocktail of sulfur dioxide, soot, and acidic droplets. Visibility dropped to barely a few feet. Buses ran with guides walking ahead carrying flares. Ambulance drivers abandoned their vehicles to feel their way on foot. But the real horror wasn't the darkness, it was what lurked in that soupy air. Coal smoke contained traces of heavy metals, carcinogens, and sulfuric acid, particles so fine they bypassed the body's defenses and lodged deep in lungs. The human toll was staggering, though slow to reveal itself. At first, hospitals noted an uptick in respiratory distress cases. Then morgues overflowed as elderly and infirm Londoners succumbed by the hundreds. Livestock at the Smithfield show gasped and collapsed, their lungs seared by the acidic haze. Even theatre performances halted mid-scene when audiences began coughing uncontrollably. Yet the most chilling detail, many residents didn't realize the scale of danger until after the wind shifted on December 9th, lifting the smog to reveal a city scarred, streets choked with the dead, undertakers overwhelmed, and funeral parlors running out of coffins. Later analysis would show mortality rates spiking to 20 times normal levels during those 5 days, with deaths continuing for months as survivors developed chronic conditions. The aftermath sparked something rare: immediate political action. Scientists quickly traced the disaster to coal combustion, particularly low-grade, nutty slack used in household heaters, a fuel so dirty it was essentially industrial waste sold to the poor. Public outrage forced Parliament to pass the Clean Air Act of 1956, banning dark smoke emissions and establishing smokeless zones where only cleaner burning fuels were permitted. Household by household, London transitioned from coal to gas and electricity, while factories installed scrubbers to filter emissions. The results were dramatic. By 1962, when another fog descended, sulfur dioxide levels had dropped by 80%. But the Great Smog's legacy extends far beyond legislation. It marked the first time a modern city confronted the existential threat of its own pollution, proving that industrialization came with invisible costs. Meteorologists began studying how weather could amplify human-made hazards, laying groundwork for today's air quality indices. Perhaps most importantly, it revealed how easily we normalize environmental degradation, how Londoners had accepted filthy air as the price of prosperity until bodies piled high forced a reckoning. When we watch footage of Beijing's greyouts or read about wildfire smoke blanketing continents, we're seeing echoes of 1952, the difference. London didn't know better, we do. The Sahel region of Africa had always known hardship, stretching south of the Sahara from Senegal to Sudan. This vast belt of semi-arid land was no stranger to dry spells. But what began in the late 1960s wasn't just another drought. It was a slow-motion environmental unraveling that would last decades, displace millions, and rewrite the map of an entire continent. By the time the rains briefly returned in the 1980s, the damage was irreversible. Farms had become dunes, pastures had baked to dust, and a new term entered the global lexicon: desertification. The roots of the crisis were both climatic and human. For centuries, nomadic herders like the Fulani and Tuareg had moved their cattle across the Sahel in sync with seasonal rains, leaving grazed land time to recover. But mid-20th century population growth and agricultural expansion disrupted this delicate balance. Governments eager to modernize promoted fixed settlements and cash crops like peanuts and cotton, which drained soil nutrients. Meanwhile, boreholes drilled to provide water for livestock allowed herds to grow beyond what the land could naturally support. When drought arrived in 1968, the overstressed ecosystem collapsed like a house of cards. Rainfall didn't just diminish, it vanished. Lake Chad, once a vital water source for 4 countries, shrank to a tenth of its 1963 size by the 1980s. The Niger River ran so low that Mali's capital, Bamako, faced water rationing. Satellite images showed the Sahara advancing southward at nearly 3 miles per year, swallowing villages whole. In Mauritania, sand dunes buried irrigation canals that had sustained agriculture since colonial times, but the most harrowing transformations were human. Across the region, subsistence farmers watched their millet and sorghum crops wither year after year. By 1973, Niger's grain harvest had dropped 65%. Starving families slaughtered their emaciated livestock, destroying both their food supply and their only asset. The mass migrations that followed reshaped West Africa's demographics. Nearly 1 million pastoralists from Mali and Burkina Faso fled south to coastal cities like Abidjan and Accra, where they faced discrimination as climate refugees. In Ethiopia's Wollo province, famine killed an estimated 40,000 in 1972 alone, a crisis captured in searing photographs that shocked the world. Yet media coverage often missed the deeper truth. This wasn't just nature's cruelty, but the culmination of policies that prioritized short-term gains over ecological limits. Scientists later identified a feedback loop that worsened the disaster. As vegetation died, the sun-baked earth reflected more heat upward, altering air currents that normally drew in moist Atlantic winds. With less rain, fewer plants grew, creating a self-perpetuating cycle of aridity. Some climatologists believe the Sahel's changed landscape may have even disrupted monsoon patterns as far away as India. What makes this tragedy so haunting isn't just the scale of suffering, but how it exemplifies humanity's fragile dance with marginal environments. The Sahel didn't just experience a drought, it crossed an invisible threshold where the land could no longer support traditional ways of life. Today, as temperatures rise and wells run dry again, the region stands as both a warning and a laboratory for survival. Farmers are reviving ancient water harvesting techniques, while projects like the Great Green Wall aim to slow desertification with a belt of drought-resistant trees. But the scars remain, because when the land changes, so does everything built upon it, not just crops and cattle, but cultures, economies, and generations of inherited wisdom. The Sahel teaches us that climate isn't just about weather. It's about the stories we lose when the earth itself forgets how to sustain them. On June 15, 1991, Mount Pinatubo in the Philippines awoke with a fury that hadn't been seen in nearly a century. After 600 years of silence, the mountain exploded with a force 10 times greater than Mount St. Helens, launching 20 million tons of sulfur dioxide straight into the stratosphere. But unlike earlier eruptions that merely shocked the world, Pinatubo did something extraordinary. It became one of the first climate events meticulously measured by modern science, offering a chilling glimpse into how we might one day deliberately manipulate the planet's thermostat. What made Pinatubo unique wasn't just its violence, but its timing. Satellites like NASA UAS orbited overhead, loaded with instruments to track atmospheric changes in real time. As the volcano's ash cloud spread like a dark umbrella across the tropics, these eyes in the sky captured every detail. Within weeks, the sulfur gases transformed into reflective sulfate aerosols, tiny mirrors that bounced sunlight back into space. The effect was immediate and measurable. By 1992, global temperatures had dropped by 0.6 degrees Celsius, a seemingly small dip, but one with dramatic consequences. Monsoon rains faltered across Asia, while the ozone layer thinned faster than expected. In the United States, the Mississippi River swelled with unusual rainfall, while Europe shivered through a year without summer, echoing the famines of 1816. Yet Pinatubo's legacy isn't just in the chaos it caused, but the possibilities it revealed. For climate scientists, it became the closest thing to a controlled experiment in geoengineering the controversial idea of deliberately cooling the planet by mimicking volcanoes. The eruption proved that sulfate aerosols could, in fact, counteract global warming, albeit with side effects. Crop yields dropped as diffuse sunlight weakened photosynthesis. Skies turned oddly hazy and sunsets glowed radioactive orange for months, but it also showed that nature's quick fix came with trade-offs we're only beginning to understand. Perhaps the most startling lesson was how long the effects lingered. Unlike ground-level pollution that washes away in weeks, Pinatubo's stratospheric veil took 2 full years to dissipate, a reminder that once we tinker with the atmosphere's chemistry, there's no instant undo button. Today, as researchers debate spraying reflective particles to buy time against climate change, Pinatubo stands as both a blueprint and a warning. Because while it proved we can cool the planet, it also asked a harder question: just because we can, should we? The answer, like the ash that once colored 90s sunsets, isn't so black and white. The year 536 dawned with a sun that refused to shine. Across Europe, Asia, and the Middle East, chroniclers recorded the same eerie phenomenon, a daytime sky so dimmed by some unseen veil that stars became visible at noon. The Byzantine historian Procopius wrote of a sun giving its light without brightness like the moon, while Irish monks described bread failing to rise and forests growing barren. For 18 terrifying months, this celestial dimming plunged the world into a cold so profound that snow fell in summer as far south as China, and crops withered in fields from Scandinavia to Mesopotamia. Modern scientists now call it the dust veil of 536, the most severe and mysterious cooling event of the last 2,000 years, one that may have rewritten the course of civilizations. What caused this global twilight? Ice cores from Greenland and Antarctica hold tantalizing clues. Layers of volcanic sulfate dating to 534 and 539 suggest not one, but 2 massive eruptions, possibly from volcanoes in Iceland or Central America, spewing enough ash into the stratosphere to block sunlight worldwide. But there's a twist. Some tree rings from this period also contain microscopic particles of extraterrestrial nickel and iron, hinting at another possible culprit, a comet or asteroid fragment exploding in Earth's atmosphere like the Tunguska event of 1908. Whether by fire from below or ice from above, the effect was the same: a planetary chill that rippled through every aspect of human life. The consequences read like scenes from an apocalyptic tale. In Scandinavia, where summer temperatures may have dropped by up to 4 degrees Celsius, entire villages starved when grain stores ran empty. Chinese records speak of mass famine in 536, followed by devastating droughts. The Byzantine Empire, already straining under Justinian's plague, saw trade networks collapse as ports froze in unseasonable cold. Even the legendary King Arthur's final battle at Camlan, as recorded in Welsh chronicles, may have unfolded against this backdrop of ecological chaos. The most startling evidence comes from the Maya lowlands, where cities like Tikal experienced abrupt political upheaval, suggesting the dust veil's reach extended clear across the Atlantic. But here's what makes this event truly extraordinary: its timing. 536 fell at the precise midpoint between the fall of Rome and the rise of Islam, a pivot in world history when old orders crumbled and new ones took shape. Some historians now argue that prolonged crop failures accelerated the decline of the Germanic Ostrogoths in Italy, paving the way for Lombard invasions. Others trace the sudden collapse of Mongolia's Rouran Khaganate to this climatic catastrophe, creating a power vacuum that would later birth the Turkic empires. Even the abrupt end of Teotihuacan's influence in Mesoamerica aligns suspiciously with this period. Climate reconstructions reveal the dust veil's staggering persistence. Tree rings show stunted growth for over a decade, suggesting not just a brief volcanic winter, but a cascade of secondary effects: failed monsoons, shifting wind patterns, and feedback loops where dying vegetation reflected even more sunlight away. The planet didn't fully recover until around 550, by which point languages, religions, and borders had redrawn themselves in the upheaval. What lingers today isn't just the mystery of what darkened the sky, but the sobering realization of how fragile our systems are. The people of 536 had no satellites to warn them, no global trade networks to buffer shortages, just the grim certainty that their world had grown colder, hungrier, and stranger by the day. In an era grappling with its own climate uncertainties, their story whispers a warning across the centuries. Sometimes the weather doesn't just change the world. It ends one world and begins another. In February 1600, a mountain in Peru began to scream, not with sound but with fire. Huaynaputina, a volcano few outside the Andes had ever heard of, tore itself apart in one of the most violent eruptions of the past 2 millennia. The blast was so powerful it sent avalanches of superheated gas and ash racing down its slopes at 200 miles per hour, incinerating villages 30 miles away. But the true devastation wouldn't be felt in South America. It would ripple across oceans and centuries, twisting global weather patterns so severely that Russian winters turned deadly, French vineyards froze solid, and peasants in Estonia starved, clutching fistfuls of rotten grain. The secret to Huaynaputina''s global reach lay in what it spewed into the stratosphere: nearly 12 cubic miles of ash and an estimated 22 million tons of sulfur dioxide. These fine particles formed a reflective blanket around the planet, scattering sunlight back into space. By 1601, temperature records from tree rings and ice cores show the northern hemisphere had plunged into the deepest freeze in 500 years. In Russia, the winter of 1601 was so bitter that wolves reportedly wandered into Moscow's streets to scavenge frozen corpses. The Baltic Sea froze so solid that merchants drove horse-drawn sledges between Sweden and Poland, a distance of nearly 100 miles over open water. Europe's wine industry became an unexpected casualty. Vineyards in Germany and France recorded harvests so late and meager that some monasteries resorted to mixing berries with their sacramental wine just to stretch supplies. Contemporary French winemakers wrote of grapes shriveling on the vine as summer frosts blackened leaves, a catastrophe memorialized in vintage notes calling 1601 the year of no wine. Even Shakespeare alluded to the strange weather in A Midsummer Night's Dream, writing of the childing autumn. Angry winter changed, but the most harrowing impact struck those already living on the edge. In Estonia and Finland, crop failures triggered famines so severe that some regions lost a third of their population. Japanese cherry blossom records show delayed blooming consistent with global cooling, while Chinese court documents describe unseasonable snowfall ruining silk harvests. Even the Jamestown colonists, struggling to establish Virginia's first permanent English settlement, faced a brutal winter they dubbed the Starving Time, likely worsened by Huanaputina's distant fury. What makes this eruption so unsettling isn't just its scale, but how it reveals the invisible threads tying the planet together. A mountain in Peru could starve peasants in Estonia, bankrupt winemakers in Bordeaux, and freeze rivers in Russia, all without anyone at the time understanding why. Modern climate models suggest temperatures didn't fully recover for nearly a decade, proving that when the Earth coughs, the whole world feels the chill. And buried in that lesson is a warning today. As we pump greenhouse gases into that same fragile atmosphere, we're conducting an experiment far more reckless than any volcanic blast. Because unlike Huanaputina's brief fury, our impact won't fade in a decade. It might define centuries. For nearly 300 years, starting around 950, the North Atlantic experienced a climatic golden age, a stretch of unusually mild weather now called the medieval warm period. Glaciers retreated, growing seasons lengthened, and sea ice melted back just enough to open corridors that had been frozen for centuries. This wasn't just a minor temperature blip, it was a planetary shift powerful enough to rearrange the chessboard of history, allowing Norse longships to reach places they never could before, while steppe horsemen found grasslands expansive enough to fuel an empire. At the western edge of Europe, the Vikings seized their moment. With less sea ice blocking northern routes, explorers like Eric the Red ventured further than anyone thought possible. In 985, he led a fleet of settlers to a place he shrewdly named Greenland, knowing the lush name would attract colonists. For a while, the marketing held truth. Ice cores drilled from Greenland's glaciers confirmed temperatures during this period were roughly 1 degree Celsius warmer than later centuries, enough to allow patches of pasture where today there's only permafrost. At its peak, the eastern settlement boasted nearly 5,000 Norse inhabitants, with farms raising cattle, sheep, and even growing barley in soil that now struggles to support lichen. Church records show Greenlanders exporting walrus ivory and wool back to Europe as late as the 1400s. Half a world away, the warming climate was rewriting history in even more dramatic fashion. On the Mongolian steppe, higher temperatures and increased rainfall extended grasslands hundreds of miles further north, a phenomenon confirmed by sediment cores from Lake Huguangma in China. This greening of the steppe meant more fodder for horses, the lifeblood of nomadic tribes. With larger herds, armies could travel farther, faster, and with greater numbers. When Genghis Khan united the Mongol clans in 1206, he didn't just benefit from brilliant strategy, he rode a wave of climatic good fortune. The lush pastures supported the tens of thousands of horses needed for his infamous cavalry, while drier conditions to the south weakened settled agricultural societies like China's Jin dynasty. Some researchers now estimate the Mongol Empire's expansion aligned so perfectly with the warm period's peak that climate may have been as crucial as leadership in creating history's largest contiguous empire. Yet the warm period's gifts were unevenly distributed. While Vikings toasted their Greenland colonies and Mongol Tumans swept across Eurasia, other regions faced punishing droughts. Tree rings from California's bristlecone pines reveal megadroughts lasting decades, while Mayan cities collapsed amid water shortages around 1100. Even Europe's good fortune had limits. Wine grapes grew in England, but warmer winters also brought malaria, carrying mosquitoes as far north as Scandinavia. What makes this era so fascinating isn't just the warmth, but how civilizations responded to it. The Norse built stone churches in Greenland that still stand today, while Mongolian horse archers used mobility to conquer an area larger than Rome at its height. Both thrived by adapting to and capitalizing on a climate that later generations would scarcely recognize. And when the warm period ended around 1300, giving way to the Little Ice Age's bitter chill, those same societies found their fortunes reversing with terrifying speed. Greenland's last known Norse writing, a wedding record from 1408, scribbled as the cold tightened its grip. The Mongols, their empire fractured as dried-up grasslands could no longer sustain vast armies. The medieval warm period stands as a stark reminder that climate isn't just scenery, it's the stage upon which human ambition either soars or stumbles. Because when the weather changes, so do the rules of the game, and the players who forget that, no matter how powerful, eventually find themselves on the wrong side of history's shifting winds. At 7:30 in the morning on June 30th, 1908, a fireball brighter than the sun tore across the sky above Siberia's remote Tunguska River basin. Witnesses nearly 40 miles away described a column of blue light splitting the heavens, followed by a shockwave so powerful it flattened 80 million trees across 800 square miles, an area larger than New York City. Windows shattered in villages hundreds of miles distant, and seismic stations across Europe recorded tremors equivalent to a 5.0 magnitude earthquake. But the true mystery of Tunguska wasn't just its violence, it was how this cataclysm from space may have left fingerprints in the very air we breathe. For decades, scientists debated what caused the explosion. A comet fragment, a stony asteroid. Modern simulations suggest it was likely a meteoroid 60 to 190 feet wide that disintegrated 5 miles above Earth's surface with the force of 10 to 15 megatons of TNT. Unlike impacts that leave craters, Tunguska's energy released entirely in the atmosphere, creating a superheated plasma jet that scorched trees below in radial patterns still visible decades later. But the most fascinating aftermath was invisible. The event likely injected hundreds of thousands of tons of water vapor and dust into the stratosphere, where high-altitude winds could spread them globally. Contemporary weather records hint at strange anomalies in the months following the blast. Europe and Asia experienced abnormally bright night skies for weeks, so luminous that newspapers in London reported midnight strolls without lanterns. This nocturnal glow matched patterns seen after massive volcanic eruptions, suggesting suspended particles high in the atmosphere were scattering sunlight. More startling were reports from California's Mount Wilson Observatory, where astronomers noted a 20% drop in atmospheric transparency lasting nearly 3 months, a dip consistent with a global veil of fine debris. Even rainfall patterns seemed affected. 1908 became one of the wettest years on record for Russia, with some climatologists speculating that Tunguska's dust may have acted as cloud condensation nuclei, supercharging storm formation. What makes this event so compelling isn't just the scale of destruction, but its eerie resemblance to modern doomsday scenarios. Had the meteoroid arrived just 4 hours later, it would have obliterated St. Petersburg. A similar airburst over Chelyabinsk in 2013, though 1,000 times weaker, still injured 1,500 people and damaged thousands of buildings. Tunguska serves as a stark reminder that space doesn't need to hit the ground to reshape our world. Sometimes the sky itself can become a weapon. And while we've gotten better at tracking near-Earth objects, the atmosphere's response remains unpredictable because when extraterrestrial debris meets our fragile blanket of air, the weather doesn't just change. It bears witness to forces beyond our control. The winter of 1952 had been unremarkable in London until December 5th, when the city woke to a fog so thick it seemed to swallow the world whole. At first, residents barely noticed. London was famous for its pea soupers, the yellowish fogs that rolled in from the Thames, but this was different. Within hours, visibility dropped to inches. Buses crawled behind conductors walking ahead with flares, their outstretched hands vanishing into the gloom. By nightfall, the air reeked of sulfur, so potent it seeped under doors and stained curtains black. What no one yet realized was that this wasn't just fog, it was a toxic cocktail of coal smoke and trapped pollution, about to become one of the deadliest environmental disasters in history. The catastrophe began with an unlucky confluence of weather and human activity. A high-pressure system settled over southern England, creating an inversion layer that acted like a lid over the city. Normally, smoke from chimneys and factories would rise and disperse, but now it became trapped near the ground, mixing with moisture to form a corrosive haze. The real danger came from what was burning: low-grade coal, rich in sulfur, pumped into the air by millions of household heaters. This wasn't industrial waste, it was the fuel of everyday life, the same coal that had warmed Londoners for generations. Only now, windless conditions concentrated it into something lethal. The first victims were the most vulnerable. Elderly residents with weak lungs collapsed in their homes. Cattle at the Smithfield Show suffocated where they stood, their airways seared by acidic particles. Ambulances sat abandoned as drivers, unable to see their own feet, groped through streets guided by building walls. Yet the full horror unfolded slowly. Morgues overflowed in the days that followed, with undertakers reporting bodies turning blue, a sign of oxygen starvation. Funeral parlors ran out of coffins. Officials initially downplayed the crisis, calling it unusual fog. But when the wind finally shifted on December 9th, lifting the smog to reveal a death toll in the thousands, denial became impossible. Modern estimates suggest up to 12,000 perished, many from respiratory failure that took weeks to claim them. London's tragedy became the world's wake-up call. Scientists quickly pinpointed the culprit: unchecked coal combustion, particularly the cheap, nutty slack burned in poor neighborhoods. Public outrage forced Parliament to act, passing the landmark Clean Air Act of 1956. The law banned dark smoke emissions, established smokeless zones, and offered grants to switch to cleaner fuels like gas and electricity. The results were dramatic. Within a decade, sulfur dioxide levels plummeted by 80%, and those iconic yellow fogs faded into memory. Other cities took note. Pittsburgh, Tokyo, and later Beijing would follow London's lead in tackling urban air quality. But the Great Smog's deepest lesson wasn't just about pollution, it was about how easily we normalized danger. Londoners had accepted filthy air as the price of warmth and progress until bodies piled high forced a reckoning. Today, when wildfires choke continents with smoke or cities grind to a halt under haze, we're seeing the same story play out on a global scale. The difference: 1952 didn't know better, we do, and that knowledge makes our choices or our silence all the heavier. The morning of April 26, 1986 dawned with an eerie quiet over Pripyat, Ukraine, a silence soon shattered by explosions that would rewrite history. As Reactor 4 of the Chernobyl nuclear power plant erupted in a fireball, it didn't just spew radiation skyward, it created its own weather. The blaze, burning at over 2,000 degrees Fahrenheit, generated thermal currents so intense they punched through the lower atmosphere, forming towering pyroconvective clouds unseen in human-made disasters before. These weren't ordinary storm clouds, they were radioactive chimneys funneling isotopes like iodine-131 and cesium-137 high enough for winds to carry them across continents. Firefighters arriving on scene faced horrors beyond flames. The radiation levels near the core, reaching 15,000 roentgens per hour, could kill a human in minutes. But the real danger lurked overhead. As water from their hoses vaporized instantly in the inferno, it condensed into steam laced with radioactive particles. This toxic mist mixed with natural rain clouds drifting in from the southeast, creating a deadly synergy. When rain began falling over Belarus just hours after the explosion, it wasn't just water soaking into the soil, it was a cocktail of isotopes that would render entire villages uninhabitable for centuries. The weather itself seemed to conspire in the disaster's spread. unusually warm spring air collided with cooler fronts, creating unstable conditions perfect for carrying contamination. Radiation readings spiked in Sweden 2 days later, not because the plume traveled in a straight line, but because shifting winds and rainout patterns painted erratic stripes of fallout across Europe. In some towns, a single thunderstorm dumped more cesium on the ground than years of nuclear testing had deposited globally. The patchwork contamination baffled scientists. One farm might be lethally hot while its neighbor remained relatively unscathed, all depending on whether radioactive rain chose to fall. What made Chernobyl's meteorological aftermath so unprecedented was the scale of human intervention. Soviet helicopters attempting to smother the blaze with sand and boron dumped over 5,000 tons of material from the sky, a desperate maneuver that inadvertently created downdrafts, forcing radioactive particles back toward the ground. Later studies found that these efforts sometimes worsened the spread, as heavier particles fell locally while lighter ones rode the winds to Scandinavia and beyond. The legacy of that poisoned rain lingers in sobering ways. Belarus's Gomel region, which received the brunt of the fallout, saw child thyroid cancer rates jump 60-fold within 5 years. Reindeer herds in Norway became so contaminated that Sami herders were forced to slaughter their livelihoods. Even today, mushrooms in Germany's Black Forest occasionally test positive for cesium from that long-ago spring. Chernobyl's lesson wasn't just about nuclear safety. It revealed how disasters don't obey borders and how the atmosphere can become an accomplice in catastrophe. Because when the sky itself turns toxic, there's no evacuation order wide enough, no shelter deep enough, just the grim understanding that some storms don't pass. They seep into the land, the water, the very cells of living things, and rewrite the future in isotopes with half-lives longer than civilizations. The summer of 2010 should have been a season of sunshine and harvest across Western Russia, but instead it became a furnace. Beginning in June, temperatures in Moscow soared past 95 degrees Fahrenheit day after day, shattering records that had stood for centuries. The air hung thick with smoke from wildfires raging through dried-out peat bogs, turning the sky a sickly orange and coating the city in a haze so dense that drivers turned on headlights at noon. By August, over 55,000 Russians would perish in the heat, hospitals overwhelmed by heat stroke and respiratory cases, while wheat fields shriveled into dust. This wasn't just a heat wave, it was a climate-driven catastrophe with ripple effects that would stretch from Russian dinner tables to protest rallies in the Middle East. What made this disaster so unprecedented was its sheer persistence. For nearly 2 months, high-pressure systems formed a blocking pattern over western Russia, a meteorological traffic jam that trapped hot air in place. Night brought little relief, with temperatures staying above 80 degrees, turning apartment buildings into ovens. Elderly residents, unable to afford air conditioning, suffered most. Morgues overflowed as cardiovascular systems failed under the strain. Meanwhile, the drought ravaged Russia's breadbasket. Grain yields plummeted by 40%, prompting the government to ban wheat exports to prevent domestic shortages. The decision sent shockwaves through global markets, where Russia supplied nearly 20% of the world's wheat. The consequences unfolded like falling dominoes. In Egypt, the world's largest wheat importer, bread prices spiked 30% overnight. Street protests erupted in Cairo, where subsidized bread feeds millions. Analysts later linked these food riots to the Arab Spring uprisings that toppled governments, an eerie case of climate change indirectly fueling revolution. Even distant markets felt the pinch. American farmers scrambled to meet demand, sending Midwest grain prices to 7-year highs. For climate scientists, the heat wave became a grim case study. A team from the Potsdam Institute later calculated that human-caused warming had made such extremes 5 times more likely, a preview of what normal summers might look like in a warmer world. Yet the most haunting lesson lay in the feedback loops the disaster exposed. The wildfires didn't just burn forests, they ignited carbon-rich peat deposits, releasing millions of tons of stored CO2 into the air. Moscow's smog, meanwhile, absorbed sunlight like a black blanket, amplifying local heating, and the withered croplands reflected more solar energy than healthy green fields, potentially prolonging the drought. Nature, it seemed, was conspiring to make bad weather worse. 2010's heat wave didn't just break records, it shattered illusions that climate change was a distant threat. Here was a crisis that killed tens of thousands, destabilized economies, and hinted at a future where weather extremes could rewrite political fortunes overnight. The Russian fields eventually recovered, the smoke cleared, and temperatures dropped, but the warning remained. In a warming world, even the weather isn't just weather anymore. It's a force that bends nations to its will. By December 2019, the skies over Sydney had turned a surreal shade of crimson, not from sunset, but from a firestorm so vast it outscaled any in recorded Australian history. The 2019 to 2020 bushfire season didn't just burn forests, it rewrote the rules of disaster, generating fire tornadoes with winds rivaling Category 3 hurricanes and pyrocumulonimbus clouds that spat lightning onto fresh tinder below. These weren't mere flames, they were self-perpetuating weather machines, twisting the atmosphere into tools of their own destruction. The scale of combustion defied belief. At its peak, the fires ravaged an area larger than Portugal, releasing enough heat to send smoke 18 miles high into the stratosphere, where winds carried it halfway around the globe. Satellite images showed plumes reaching South America, while New Zealand's Franz Josef Glacier, over 1,000 miles away, turned caramel brown under a blanket of ash. Skiers in alpine resorts found themselves carving through grimy snow tinged with the remnants of incinerated eucalyptus. But the most terrifying innovations came from the fire's ability to manipulate their own environment. Superheated air rising from the infernos spawned towering pyrocumulonimbus clouds, a rare phenomenon where smoke and moisture collided to form thunderstorms devoid of rain. Instead of quenching flames, these clouds hurled dry lightning strikes that ignited new fires miles ahead of the main blaze. In one documented case near Canberra, a fire-generated tornado with winds exceeding 150 miles per hour flipped 10-ton trucks like toy cars, a grim reminder that nature's fury could weaponize even the air itself. The ecological toll was staggering. An estimated 3 billion animals perished or were displaced, kangaroos fleeing walls of flame, koalas with singed paws gulping water from rescue volunteers' bottles. The soot that reached New Zealand's glaciers had a darker legacy still. By darkening the ice, it accelerated melting as the polluted snow absorbed more sunlight. Scientists later calculated that the fires released 900 million tons of carbon dioxide, more than Australia's annual fossil fuel emissions, creating a feedback loop where climate change fueled disasters that then worsened climate change. What made this catastrophe so haunting wasn't just its violence, but its foreshadowing. These weren't ordinary bushfires, they were a preview of a world where extreme heat, drought, and wind conspire to create disasters beyond traditional frameworks of control. When firefighters reported flames leaping across 8-lane highways or witnessed trees exploding from sap boiling within, they weren't just battling a fire, they were confronting a new era where the weather doesn't just enable disasters. It becomes one. On January 15, 2022, the South Pacific Ocean erupted with a force that defied all expectations. The Hunga Tonga Hunga Hapai volcano, previously a little-known seamount between two small islands, unleashed the most powerful explosion the planet had witnessed in over a century. The blast sent shockwaves circling the globe not once, but 4 times, a phenomenon last observed with Krakatoa in 1883. But what made this eruption truly unprecedented wasn't just its raw power. It was the colossal volume of water it hurled into Earth's fragile atmosphere, an event that may subtly rewrite weather patterns worldwide for years to come. Unlike typical volcanic eruptions that spew ash and sulfur dioxide, Hunga Tonga's underwater detonation vaporized an estimated 146 million tons of seawater in an instant. Satellite readings later revealed something astonishing. This single event increased the stratosphere's water vapor content by an unprecedented 10%. To grasp the scale, imagine dumping the water from 58,000 Olympic-sized swimming pools into the upper atmosphere all at once. That vapor didn't just dissipate, it joined an invisible river of high-altitude moisture that will likely take 5 to 10 years to fully dissipate. Scientists were stunned. No eruption in the modern satellite era had ever pumped so much H2O into the sky. The consequences of this atmospheric intrusion are still unfolding. Water vapor is Earth's most abundant greenhouse gas, and while it typically cycles out of the lower atmosphere in days, stratospheric water can linger for years. Early climate models suggest Hunga Tonga's eruption might temporarily nudge global temperatures upward by a few hundredths of a degree, not enough to notice day to day, but significant on a planetary scale. More concerning is how this moisture could interact with ozone chemistry. Water molecules in the stratosphere can break down protective ozone and even form polar stratospheric clouds that accelerate ozone depletion, a process usually associated with frigid Arctic winters, not tropical eruptions. Weather patterns may feel the eruption's fingerprints too. Some researchers speculate the extra water vapor could intensify rainfall in certain regions while drying others, though these effects would likely be subtle and mixed with natural variability. The Southern Hemisphere's 2022 cyclone season showed unusually early activity, with tropical storms forming months ahead of schedule, a pattern some scientists cautiously link to Hunga Tonga's atmospheric disturbance. Satellite operators have also noted increased drag on low-orbiting spacecraft as the expanded water vapor subtly thickens the upper atmosphere, forcing satellites to burn extra fuel to maintain orbit. What makes Hunga Tonga's legacy so fascinating is how it challenges our understanding of volcanic impacts. For decades, scientists focused on sulfur dioxide's cooling effects like Pinatubo's famous global chill. But this eruption barely produced any sulfur. Instead, it highlighted water's overlooked role in atmospheric chemistry, proving that volcanoes don't just cool the planet, they can potentially warm it too under the right conditions. As monitoring continues, each new dataset reveals another layer of complexity in how Earth systems respond to such violent interventions. The eruption's most haunting lesson might be its timing. Coming just as humanity struggles to rein in greenhouse gas emissions, Hunga Tonga offered a sobering preview, a natural experiment in rapid atmospheric alteration. Because while we debate carbon budgets and emission targets, the planet reminds us that it too can change the game overnight with forces far beyond our control. The difference is when nature decides to tweak the thermostat, it doesn't ask permission, it just explodes. Around 6200 BC, the world shuddered under a climate shock that would ripple across continents for centuries. Imagine the scene: glacial meltwater trapped for millennia behind ice dams in North America suddenly found an escape route. The collapse of these icy barriers unleashed a deluge equivalent to 15 Lake Superiors, a pulse of freshwater so vast it poured into the North Atlantic like a planetary-scale faucet left running. Scientists now call this the 8.2 kiloyear event, named for its geological timestamp, a climatic turning point buried in ice cores and ocean sediments that tells a story of civilizations upended by a changing sky. The mechanics of this disaster read like a slow-motion catastrophe. As the last ice age retreated, Canada's Agassiz and Ojibwe glacial lakes, some larger than modern-day Ukraine, sat trapped behind walls of ice. When warming temperatures finally breached these frozen dams, the release was catastrophic. Freshwater flooded into the Labrador Sea at rates exceeding 10 Amazon rivers combined, forming a buoyant lid atop the saltwater. This layer acted like a chemical fire extinguisher on the Atlantic meridional overturning circulation, the great oceanic conveyor belt that carries warm water northward. With this vital heat pump weakened, temperatures across the northern hemisphere plummeted within decades. Ice cores from Greenland show oxygen isotope ratios plummeting, revealing a cold snap that lasted at least 160 years, a geological blink of an eye, but several human generations of suffering. The human cost emerges from archaeological whispers across the devastated landscapes. In Mesopotamia's northern fringes, the thriving Halaf culture abruptly abandoned their distinctive circular houses, their elegant pottery styles vanishing as if erased. Along Europe's Atlantic coast, Neolithic farmers deserted settlements near modern-day Doggerland as rising seas, already climbing from melting glaciers, accelerated their advance. The most haunting evidence comes from beneath the English Channel, where drowned forests from this period still stand as ghostly monuments to drowned worlds. Tree rings from German oaks tell the same story: years of stunted growth exactly matching the 8.2 kiloyear chill, their cramped annual bands whispering of failed harvests. Yet some communities didn't just endure, they adapted in ways that reshaped history. In Egypt's Nile Valley, where the flood cycle became erratic, people developed new irrigation techniques to buffer against drought. This technological leap may have planted the seeds for pharaonic agriculture. Meanwhile, in Çatalhöyük, the famous Anatolian proto-city shows signs of increased grain storage during these precarious centuries, evidence of societies learning to hedge against climate's whims. The very concept of centralized food reserves might trace its origins to this crisis. What makes this event so pivotal isn't just the cooling, but its timing at civilization's dawn. Just as humanity was transitioning from nomadic life to permanent settlements, the climate pulled the rug from beneath our feet. The 8.2 kiloyear event serves as a brutal reminder that our species' greatest achievements, cities, agriculture, complex society, were forged not in some golden age of stability, but in the teeth of climatic chaos. And buried in that lesson is an uncomfortable truth we're grappling with today. Civilization didn't arise despite climate change, it arose because of it. The difference now is that instead of ice dams breaking, we're the ones turning the planetary thermostat, with consequences we're only beginning to comprehend. Around 1628 BC, the island of Thera, now known as Santorini, exploded with a violence that reshaped the ancient world. The eruption was so colossal it tore the island apart, leaving behind a smoldering caldera where a thriving Minoan settlement had once stood. But the destruction wasn't confined to the Aegean. Ash and sulfur dioxide surged miles into the stratosphere, casting a shadow that stretched from Egypt to China. Tree rings from Irish bogs to Californian sequoias tell the same story, a sudden, sharp, cold snap in the years that followed, as the volcano's veil dimmed the sun's warmth across the globe. The scale of Thera's fury defies modern comparison. Estimates suggest it was 4 times more powerful than Krakatoa's 1883 blast, with pyroclastic flows racing across the sea at 100 miles per hour to scorch nearby Crete. Tsunamis 40 feet high smashed into coastal cities, their force so immense that geologists still find traces of Thera's pumice in Nile Delta sediment cores. Yet the most far-reaching impact was atmospheric. Ice cores from Greenland contain sulfate spikes dating precisely to this period, chemical fingerprints of Thera's pollution drifting over the Arctic. Chinese astronomers of the Shang dynasty later recorded strange, dimmed sunlight, while Egyptian papyrus allude to 10 days of darkness, likely as ash clouds blotted out the sky. This climatic chaos may have birthed one of history's most enduring legends. Centuries later, Plato's dialogues Timaeus and Critias described a utopian island called Atlantis, which sank beneath the waves in a single day and night. The parallels are striking. Thera's circular caldera matches Plato's description of concentric city rings, while the eruption's tsunamis align with his accounts of catastrophic flooding. Even the timeline fits. Egyptian priests Plato cited as sources could have passed down garbled memories of Thera's devastation. Whether Atlantis was pure fiction or a distorted echo of this real disaster remains debated, but the eruption's cultural aftershocks are undeniable. Minoan art shifted abruptly from vibrant frescoes to somber funerary motifs, suggesting a society grappling with existential trauma. Thera's true legacy, though, lies in its demonstration of how climate and myth intertwine. A single volcanic tantrum didn't just lower global temperatures, it seeded stories that would haunt humanity's imagination for millennia. And that duality of measurable science and unfathomable folklore captures the real power of history's weather-altering moments. They don't just change the sky, they change how we see ourselves in its shadow. The Seine had always been Paris's lifeblood until January 1910, when it became the city's tormentor. After months of relentless rain, the river swelled beyond recognition, bursting its banks with a force that turned cobblestone boulevards into canals and transformed the city of light into a murky, waterlogged shadow of itself. By January 28, the floodwaters reached 26 feet above normal levels, submerging entire neighborhoods up to their second-story windows. The Louvre's curators scrambled to relocate masterpieces from basement storage as water seeped into galleries, while the metro's shiny new tunnels, pride of the modern age, filled like bathtubs, paralyzing the city's transit for months. But this disaster wasn't just about submerged streets. It forced Europe to confront how little they understood the very weather patterns that could undo their grandest cities overnight. Paris's vulnerability lay in its own beauty. Centuries of development had straightened and confined the Seine with stone quays, maximizing real estate but eliminating natural floodplains that once absorbed excess water. When the rains came, and they came with biblical intensity that winter nowhere remained for the river to go but up, the statistics still stun. Over 500 million cubic meters of water inundated the city, enough to fill 200,000 Olympic swimming pools. The zinc rooftops that gave Paris its iconic gray silhouette became makeshift boats floating away on the current. Even the city's famed bookstores along the quays broke free from their moorings, their literary treasures dissolving into pulp downstream. The flood's aftermath birthed two revolutions, one technological, one bureaucratic. Meteorologists across Europe suddenly faced uncomfortable questions. Why had weeks of abnormal rainfall not triggered earlier warnings? The crisis spurred innovations in continental weather monitoring, linking observation stations via telegraph to track storms moving across borders. France established its first centralized flood prediction service by 1919, using river gauges and rainfall data to forecast surges. But the deeper change was philosophical. Urban planners recognized that taming rivers with brute force engineering often backfired catastrophically. Berlin and Prague studied Paris's ordeal, implementing expansive riverside parks designed to flood safely during surges, a concept now standard in modern cities from Seattle to Singapore. Perhaps the most enduring legacy lies beneath today's Parisian streets. After the waters receded, engineers discovered the flood had exploited a forgotten network of medieval limestone quarries turned sewers beneath the city. This led to a massive mapping and reinforcement project, creating the resilient underground labyrinth that now supports Paris's infrastructure. Even the city's famous street-level plaques marking the 1910 flood's high points serve a dual purpose. They're both historical markers and subtle warnings to future generations about the Seine's hidden power. What makes this disaster so pivotal isn't just the spectacle of a drowned metropolis, but how it revealed the arrogance of assuming nature could be fully controlled. The flood didn't just change Paris, it reshaped how cities worldwide coexist with the waterways that nourish and threaten them. Because when the Seine reclaimed its ancient pathways that winter, it didn't just rise. It taught humanity a humbling lesson about the price of forgetting where the water wants to go. In 1859, a wealthy English settler named Thomas Austin released 24 rabbits onto his Australian estate near Geelong, envisioning nothing more than a nostalgic touch of home, a bit of sport hunting like back in Britain. Within decades, that small act would unleash an ecological catastrophe so vast it reshaped the continent's climate itself. The rabbits, finding no natural predators and an endless buffet of native vegetation, exploded into a plague of biblical proportions. By the 1930s, their population surpassed 10 billion, chewing through an area the size of Western Europe and leaving behind a landscape so barren it altered the very weather patterns overhead. The mechanism of this environmental unraveling was deceptively simple: teeth meeting roots. Rabbits excel at grazing to the ground, consuming not just grass but the seedlings of shrubs and trees that would normally regenerate. As they denuded vast swaths of land, the bare soil lost its ability to retain moisture. Winds that once rustled through dense scrub now whipped up dust storms, carrying topsoil away in great ochre clouds. Without plant cover to release water vapor through transpiration, local humidity dropped. The result, a self-perpetuating cycle of aridification where once fertile regions began resembling deserts. In South Australia's semi-arid zones, rainfall declined by as much as 40% in affected areas, not because clouds vanished, but because the land could no longer sustain the delicate microclimates that once coaxed rain from the sky. Scientists later identified a chilling feedback loop. The rabbits' destruction of deep-rooted perennial plants allowed shallow-rooted annuals to take over, which died off quickly after rains, leaving the soil exposed. This amplified the heat island effect, where sunlight baked the unprotected earth, creating rising hot air that actually pushed moisture-bearing clouds away. Satellite imagery decades later would show stark differences in ground temperatures between rabbit-ravaged areas and regions where native vegetation held firm, proof that the plague hadn't just changed the land, it had reprogrammed the atmosphere above it. The most haunting case study emerged in the Murray-Darling Basin, Australia's breadbasket, where emus and kangaroos once moved through mosaic landscapes of grass and shrubs. Rabbits created monocultures of dust. Farmers watched helplessly as their fields and the rains that sustained them vanished. By 1950, an area larger than Germany had been transformed into rabbit deserts, with some regions taking 50 years to recover even after biocontrols like the myxoma virus were introduced. The irony was cruel. Settlers had tried to remake Australia in Europe's image, only to create a wasteland unlike anything on Earth. This wasn't just an invasion. It was a living experiment in how creatures we dismiss as harmless can become architects of climate when unleashed in the wrong place. Because when billions of hungry mouths strip a continent bare, they don't just leave footprints in the soil. They leave fingerprints on the sky itself. The monsoon rains came to Bangladesh in the summer of 1974 as they had for millennia, but this time the heavens opened with unrelenting fury. From June through September, the Brahmaputra and Ganges rivers swelled beyond all historical records, fed by rainfall measuring over 150% of normal levels. Yet the rising waters weren't the only culprit in the catastrophe that followed. Decades of deforestation in the Himalayas had stripped away nature's protective buffer, turning seasonal floods into a tidal wave of mud and debris that submerged 70% of the country. Upstream in Nepal and India, logging operations had cleared vast swaths of ancient forests that once acted like giant sponges, absorbing rainfall and releasing it slowly. With their roots no longer anchoring the soil, monsoon runoff barreled downhill unchecked, carrying millions of tons of sediment into Bangladesh's river channels. Satellite images from that year reveal a sickening transformation. Once clear waterways choked brown with silt, their beds rising so high that even modest rains triggered overflows. Farmers who had relied on predictable flood cycles for rice cultivation now watched helplessly as their fields vanished under churning currents that refused to recede. The human toll defied comprehension. Traditional bamboo huts dissolved like sugar cubes in the currents, while makeshift rafts cobbled from banana trees became the only refuge for families clinging to life. In the district of Rangpur alone, floodwaters stranded over 1 million people without food or clean water for weeks. Cholera and dysentery raced through overcrowded relief camps where survivors queued for hours under blistering sun to receive a single cup of rice. By December, official death tolls surpassed 26,000, though aid workers estimated the real number, including disease and starvation, likely exceeded 300,000. What made this disaster so devastating was the collision of natural fury and human short-sightedness. Meteorologists later determined the 1974 monsoon wasn't statistically more intense than others in the 20th century, but without forests to temper its impact, the rains became a weapon. Hydrologists coined the term sedimentary cascade to describe how deforested slopes amplified destruction, with each ton of eroded soil reducing river capacity and heightening future flood risks. The same waters that once nourished Bengal's legendary rice paddies now drowned them under suffocating layers of silt, rendering once fertile plots barren for years. Yet from this tragedy emerged unexpected innovations. Bangladeshi engineers pioneered raised homesteads on earthen platforms, while farmers adopted floating gardens, rafts of water hyacinth topped with soil, to grow vegetables even in flooded areas. The disaster also spurred the creation of the world's most sophisticated flood forecasting system, combining river gauges, satellite data, and community alerts to save countless lives in later monsoons. The legacy of 1974 isn't just etched in memorial stones across Bangladesh's floodplains. It serves as a brutal lesson in how human actions, whether chainsaws in distant mountains or decisions in distant capitals, can twist nature's rhythms into catastrophe. Because when the trees vanish, the rain doesn't just fall, it hunts. The summer of 2003 should have been a season of sun-drenched bliss across Europe, but instead it turned into a silent massacre. By early August, thermometers from Portugal to Germany were shattering all-time records, with Paris hitting 104 degrees Fahrenheit, a temperature the city's medieval infrastructure was never built to endure. Pensioners wilted in un-air-conditioned apartments, their bodies failing as nighttime temperatures stayed stubbornly in the 90s, offering no respite. Rivers like the Loire evaporated to trickles, exposing centuries-old hunger stones carved with warnings from past droughts. And when the heat finally broke in late August, the death toll stood at over 70,000, more than some wars claim in years of fighting. What made this heat wave so deadly wasn't just the mercury's climb, but Europe's complacency. Unlike American or Middle Eastern cities accustomed to scorching summers, many European capitals lacked basic cooling infrastructure. In France, where over 14,000 perished, buildings designed to retain heat became death traps, their thick stone walls baking like ovens. Hospitals overflowed with heatstroke victims as morgues ran out of space, stacking bodies in refrigerated trucks commandeered from supermarkets. The crisis exposed brutal inequalities. Elderly women living alone in attic apartments died unnoticed for days, while wealthier families fled to countryside villas or installed makeshift air conditioners. The aftermath sparked a reckoning. France implemented a nationwide heatwave plan within a year, including registries to check on vulnerable citizens and mandatory cool rooms in nursing homes. Cities like Lyon began painting rooftops white to reflect sunlight, while Vienna planted thousands of trees to create urban shade corridors. Meteorologists developed new early warning systems, recognizing that fatalities begin climbing well before official heat wave thresholds are crossed. Perhaps most tellingly, Europeans abandoned their traditional skepticism of air conditioning. Sales in Italy jumped 600% by 2010. Yet the 2003 disaster's deepest legacy lies in what it revealed about climate change's uneven toll. The same heat wave that killed thousands in Paris caused barely a ripple in Cairo or Phoenix, where adaptation was baked into culture and infrastructure. Europe learned the hard way that climate vulnerability isn't just about geography, it's about memory. When your civilization evolves across temperate centuries, the first time the thermostat spikes, the bodies fall. And that lesson now echoes globally as places once shielded by mild climates face a future where unprecedented heat becomes the norm. The tsunami that struck Japan's Fukushima Daiichi nuclear plant on March 11, 2011, didn't just trigger meltdowns, it birthed a meteorological nightmare. As reactor buildings exploded and radioactive material spewed into the air, emergency crews faced an impossible dilemma. Spray seawater to cool the cores and risk contaminated runoff, or let the cores overheat further. But the real crisis came when shifting winds transformed the disaster site into a toxic weather machine, proving that when nuclear accidents collide with atmospheric forces, the rules of containment no longer apply. Within days of the tsunami, firefighters unleashed torrents of water onto the overheating reactors, nearly 40,000 tons in the first week alone. All that liquid had to go somewhere. Steam billowing from the wreckage carried cesium and iodine isotopes into low-lying clouds, while runoff pooled in the plant's basement, mixing with radioactive debris to form a hazardous sludge. Then came the rain. Spring showers in late March washed airborne particles back to Earth, creating unpredictable hotspots miles from the facility where radiation levels spiked without warning. Helicopters measuring radiation from above detected plumes twisting like ghostly snakes across the countryside, impossible to predict, governed by the whims of sea breezes colliding with inland air currents. The most surreal phenomenon occurred when the plant's own cooling efforts inadvertently created microclimates. As emergency crews doused reactors, evaporating water formed localized fog banks laced with radioactive droplets, an eerie weather system contained entirely within the disaster zone. Satellite imagery showed these artificial clouds drifting northeast toward the Pacific, sparing Tokyo but raising alarms about marine contamination. Meanwhile, desperate attempts to prevent hydrogen explosions involved venting radioactive steam directly into the atmosphere, a controlled release that still scattered isotopes as far as California within days. Beyond the immediate chaos, Fukushima reshaped global energy debates overnight. Germany shocked the world by announcing a full nuclear phase-out within 11 years, a decision directly attributed to watching Japan struggle with radioactive rain. China froze new reactor approvals for 2 years while U.S. regulators scrambled to reassess flood risks at coastal plants. Even France, which derives 70% of its electricity from nuclear power, saw public support drop below 50% for the first time in decades. The disaster exposed a chilling truth. Nuclear safety isn't just about engineering, it's about anticipating how weather can turn containment protocols into cruel jokes when winds shift or clouds decide to open up. Perhaps the most haunting legacy lies in Fukushima's lingering uncertainties. Scientists still debate whether the Pacific's Kuroshio current dispersed most radiation harmlessly or created underwater plumes we've yet to track fully. Farmers near the plant watch weather forecasts with newfound dread, knowing a summer downpour could reawaken dormant isotopes in their fields, and meteorologists now include radiation dispersion models in disaster protocols, a grim addition to the forecast that turns every cloud into a potential threat. Because when the air itself becomes radioactive, the weather doesn't just happen to us, we become part of its unfolding story for generations to come. On August 25, 2017, Hurricane Harvey made landfall near Rockport, Texas, with winds howling at 130 miles per hour, but the real devastation came after the storm stalled. Instead of moving inland and weakening like typical hurricanes, Harvey parked itself over Houston for 4 agonizing days, wringing every drop of moisture from the Gulf of Mexico onto the sprawling metropolis below. The numbers still defy belief. Over 60 inches of rain in some neighborhoods, enough to submerge a 6-story building if it had fallen all at once. But what made Harvey historic wasn't just the rainfall totals. It was how this disaster exposed the fragile illusions of flood control in the modern age, forcing engineers to rewrite the rulebook on urban survival in an era of climate extremes. Houston's vulnerability lay hidden in its very geography. Built on a flat coastal plain crisscrossed by bayous, the city had long relied on these natural drainage channels to handle routine storms. Decades of unchecked development had paved over nearly 200 square miles of prairie land that once absorbed rainfall like a sponge, replacing it with concrete that sent water racing straight into overflowing channels. Compounding the crisis, 2 massive reservoirs built in the 1940s to protect downtown reached capacity and began spilling uncontrolled torrents into already flooded neighborhoods. The horrific result: 80,000 flooded homes, 30,000 displaced residents, and streets transformed into brown, swirling rivers where base boats replaced ambulances in rescue efforts. The aftermath sparked an engineering revolution. Traditional flood maps based on century-old rainfall data were suddenly obsolete, forcing the Federal Emergency Management Agency to introduce unprecedented, rainfall-driven flood models. Houston launched a $2.5 billion bond program to buy out flood-prone homes, not to rebuild, but to demolish them and restore natural floodplains. Architects began elevating new constructions on stilts, while resilience hubs with backup power and supplies were strategically placed across vulnerable communities. The most startling innovation came from the Netherlands, where Houston engineers studied Amsterdam's flood-proof building structures with floating foundations that rise with floodwaters like boats at anchor. Harvey's most haunting legacy wasn't just the water it poured down, but the warning it wrote across the sky. Scientists later calculated that climate change had made such extreme rainfall 3 times more likely, as warmer Gulf waters turbocharged the storm's moisture capacity. When Harvey finally drifted away on August 29th, it left behind a sobering blueprint for 21st century disasters, where the greatest threat isn't the storm's fury, but humanity's failure to anticipate just how fiercely the weather can rewrite the rules. By August 2020, California was already smoldering under a record-breaking heatwave when a lightning storm unlike any other descended upon the state. Except these bolts didn't come from the sky. They erupted from the fires themselves. The August complex fire, fueled by desiccated vegetation and hurricane-force winds, didn't just burn. It engineered its own weather system, spawning towering pyrocumulonimbus clouds capable of hurling lightning miles ahead of the fire front. These weren't mere flames, they were self-perpetuating storms, twisting physics to accelerate their own destruction in a terrifying feedback loop. The science behind these fire-generated thunderstorms reads like something from a dystopian novel. As the inferno raged, superheated air shot upward at speeds rivaling volcanic eruptions, carrying smoke and moisture high into the atmosphere. At altitudes where temperatures plummet, the moisture condensed around ash particles, forming colossal clouds that reached 12 miles high, higher than Mount Everest. Inside these pyro-CBS, ice crystals collided with soot, creating static charges powerful enough to generate lightning without any rain. The result: dry lightning strikes that ignited new fires well beyond the original burn zone, allowing the blaze to leapfrog firebreaks and containment lines with ruthless efficiency. Satellite imagery from that summer reveals the surreal scale of this phenomenon. The El Niño lightning complex fire alone produced 50 pyro-CBS in just 72 hours, each one functioning like a thunderstorm crossed with a flamethrower. One particularly monstrous cell near Lake Tahoe generated over 1,000 lightning strikes in 60 minutes, sparking secondary fires that merged into a single catastrophic mega blaze. Firefighters described watching in horror as anvils of smoke and cloud collapsed under their own weight, creating hurricane-force downdrafts that hurled embers like artillery shells. These fire tornadoes reached speeds of 140 miles per hour, strong enough to flip 10-ton fire trucks, while temperatures at their cores exceeded 2,700 degrees Fahrenheit, hot enough to vaporize aluminum engine blocks. The ecological domino effect was staggering. Smoke particulates from these pyrocumulonimbus clouds reached the stratosphere, where they lingered for months, drifting as far as Europe and coloring sunsets blood red over New York City. The soot that settled on Sierra Nevada snowpack accelerated melting by absorbing sunlight, exacerbating California's drought cycle. Meanwhile, the fire's CO2 emissions in 2020 alone equaled the annual output of 6 million cars, a grim reminder that climate change isn't just fueling disasters, it's being fueled by them in return. What made the 2020 fires so chilling wasn't just their intensity, but their intelligence. These weren't random acts of nature. They were firestorms that weaponized the atmosphere against itself, using wind, lightning, and even gravity to outmaneuver human firefighters. When a single blaze can spawn weather systems that birth new fires miles away, we're no longer battling flames, we're negotiating with an entirely new kind of climate beast. And as temperatures keep rising, these pyro-CBS aren't just California's problem. They're a preview of fire seasons to come, where the line between weather and wildfire blurs into something far more dangerous. The Arctic is warming at nearly 4 times the global average, a phenomenon scientists grimly call Arctic amplification. But this isn't just a regional crisis, it's rewriting weather patterns across the entire northern hemisphere in ways we're only beginning to understand. Picture Earth's climate as a delicate mobile, tug on one part and the whole structure shudders. Right now, the Arctic is that disruptive pull, sending shockwaves through jet streams and storm tracks that shape weather from New York to Beijing. At the heart of this disruption lies a simple but deadly feedback loop. As Arctic sea ice vanishes, losing nearly 13% of its volume per decade, dark ocean water absorbs sunlight that once reflected off bright ice. This extra heat weakens the polar vortex, the high-altitude wind current that traditionally corrals cold air near the pole. Like a wobbling top, the weakened vortex begins to kink and buckle, sending frigid air plunging southward while warmer mid-latitude air surges north. The result, bizarre weather whiplash. Texas freezes under snow while parts of Siberia bake in unseasonable warmth. These jet stream contortions don't just cause extreme cold snaps. They create stuck weather patterns that turn bad conditions into disasters. When the jet stream slows, as it increasingly does, high and low pressure systems linger like uninvited guests. A rainy spell becomes floods, a dry stretch metastasizes into drought. In 2018, a stalled high-pressure system over Europe turned the continent into a furnace, sparking wildfires in Sweden's Arctic Circle and wilting Germany's wheat harvest. That same summer, California's ridiculously resilient ridge, a stubborn high-pressure zone, blocked Pacific storms for months, intensifying the state's worst wildfire season on record. The most unsettling changes may be happening over the ocean. As Arctic waters warm, the temperature gradient between pole and equator softens the engine that drives global wind patterns. Some climatologists believe this is already altering the North Atlantic circulation, potentially explaining why hurricanes now crawl along coasts like Harvey in 2017, dumping unprecedented rain. Others point to disrupted monsoons in India, where warmer Arctic conditions may be sapping the thermal contrast that draws monsoon winds inland. Yet the scariest possibility lies buried in Arctic permafrost. As it thaws, ancient methane, a greenhouse gas 30 times more potent than CO2, bubbles up through Siberian lakes. Early signs suggest this could accelerate warming further, tightening the feedback loop. Meanwhile, Greenland's melting ice sheet dumps freshwater into the North Atlantic, potentially slowing the Gulf Stream, a scenario that could paradoxically cool parts of Europe while the rest of the planet overheats. What makes Arctic amplification so destabilizing isn't just the science, it's the uncertainty. We've entered an era where the old rules no longer apply, where the once reliable rhythms of seasons and storms grow erratic. The Arctic's fever is Earth's fever, and until we break that cycle, the weather we once knew may exist only in history books, and the forecasts of tomorrow may defy everything we thought possible. From volcanic eruptions that plunged continents into winter, to industrial smokestacks that rewrote the planet's atmospheric chemistry, history reveals an undeniable truth: humanity and nature have always been co-authors of Earth's climate story. The 30 events we've explored aren't just isolated disasters, they're chapters in a grander narrative where small actions cascade into planetary consequences. Whether it was colonists unwittingly cooling the globe by wiping out indigenous farmers, or coal-fired factories warming it with the relentless burning of ancient carbon, our fingerprints have been on the thermostat far longer than we've acknowledged. Yet this retrospective holds urgent lessons for our current crossroads. The same forces that once triggered accidental climate shifts, deforestation, pollution, reckless land use now operate at scales our ancestors couldn't fathom. Where Tambora's explosion cooled the Earth for 3 years, modern industry does the opposite every single day. Where the Little Ice Age altered harvests and toppled empires, today's warming threatens supply chains, megacities, and entire ecosystems. The difference: past societies faced climate surprises. We're barreling toward a crisis with eyes wide open, armed with centuries of evidence about cause and effect. But history also offers hope in its patterns of resilience and reinvention. The Dust Bowl birthed soil conservation science. London's Great Smog sparked clean air revolutions. Even the darkest climate shocks carried seeds of adaptation, whether Norse farmers learning to store more grain or modern architects designing flood-proof cities. Our ancestors lacked satellites and climate models, yet they adjusted their sails to survive nature's shifts. Today, with exponentially greater knowledge and technology, we're not powerless passengers on this journey, we're navigators. So as we stand at the edge of our own climate reckoning, let's remember, the weather isn't just something that happens to us. It's a mirror reflecting our choices, a conversation between human ambition and planetary systems. The next chapter hasn't been written yet. Will it be one of continued disruption or of innovative coexistence? The answer lies not in the stars, but in the collective story we choose to tell. One decision, one innovation, one changed weather pattern at a